Hello, today we're going to talk about ADAS, Advanced Driver Assistance Systems. And the big question for the aftermarket is it really chaos or is it an opportunity? Well, as we'll find out, it's a bit of both. Well, today we're going to talk about 4 subject areas. The vehicle defense system, that's what ADAS is. It helps defend our vehicle from being hit by others or other objects. We're going to talk about the sensors involved and how to aim them, and we're going to look at some of the processes around that. And we're going to talk about the future, and then finally what's in it for us. What I'd like to begin with is a very important point. Frequently, ADAS is mentioned in the same breath as autonomy. Autonomy is not ADAS. Autonomy builds on the features of ADAS, but ADAS is a defense system. Autonomy, the ultimate objective, is that we would sit behind or inside a cabin and not touch a single control, give the vehicle some idea of where we want to go and get out at the other end of the journey. That's the goal. And this is a long way from this. Throughout, the driver behind the wheel is responsible for the vehicle, whether the systems around him or her malfunction or not. Let's start with what that defense system is. So we have an array of sensors. And we'll start with the very first part of the confusion. Not all vehicles have all sensors. Not all sensors have the same performance. And yet, glibly, they have the same label, ADAS. So we need to think about where those sensors could be and go looking for them, because even now, they can be an option fit. They're not necessarily standard equipment. That is changing rapidly. But much of this technology has been around since the early 2000s in tiny numbers, and those numbers are increasing rapidly. And that is due to imminent standardization through law. That's coming. It's already come to HGVs and passenger carrying vehicles above 7.5 tons. That was in 2015. It's coming to light commercial vehicles in 2018. It's projected to come as standard equipment requirement for passenger cars by 2022 here in Europe. So we have, going round the vehicle at the very front, typically located at the very front, just behind the grille or the bumper, is a radar. And that radar can have multiple ranges. So it has almost a single power output, which can either be focused in a very narrow cone angle for a range of up to 250 meters, or in a wider cone angle that can be down towards 30 to 40 meters, and any combination in between. Also, the box, the radar itself, is solid state. That's a revolution that came from the military world, but it can have multiple range radar units inside a single module. These units are notoriously expensive in terms of retail. They can be damaged if they're dropped from bumper height onto the ground by accident. Indeed, some manufacturers recommend should be replaced. Don't chance it. We're going to talk about how those are aimed in a little bit. If we move up towards the windscreen, we'll find some sensors there. There is the light and rain sensor that has existed for many years, and usually next to it can be a camera, and that camera can either have a single lens or 2 lenses. And the range there is about 0.5 kilometer. So unlike the radar, which is detecting objects ahead of the vehicle and measuring the distance to it, the camera is classifying. Again, this is technology that came from military, and it allows the camera to classify from around 1,200 different objects what it can be. Is it a vehicle? Is it a car? Is it a truck? Is it a lump of rock? Is it an animal? And it tracks, having classified what that object is, it tracks it in its path across the intended path of direction for our vehicle. We then have sometimes next to it a short range measurement device, LiDAR, which can have a range of typically 10 meters or less. And this is used again to measure the distance between our vehicle and potential obstructions ahead. And this is used as infill for radar, but it isn't necessarily fitted. Sometimes it's there, sometimes it's not. As we go around the vehicle, we can find that our parking sensors have had a second breath of life. And here we see them pointing sideways with a 4.5 meter range, and this is used for determining the space that's available for parking, for automated parking. Some manufacturers, for example Tesla, use it as a means of detecting vehicles that are in the blind spot. This, you can see 4.5 meters is not very long distance, and therefore not much time. So it has very limited capability in that sense. However, for normal blind spot detection, it's either based on optic, based in the door mirrors, or radar, again, mounted at the rear, normally just behind the rear wheels, behind the bumper skin. And then at the back, we can have radar. We can also have a reversing camera, which neatly, by hooking it into the data system for the braking system, gives us auto brake if we reverse out of a parking place and a vehicle or a person crosses the rear of the vehicle. So we have a variety of distances, ranges and devices, and a vehicle which could have them may not have any. And that's what we have to bear in mind when we think about what we're looking for, because crucially the data that describes VIN versus registration mark versus spec usually doesn't include the options that we use to build the vehicle unless we go to the vehicle manufacturer's website, and even then not all vehicle manufacturers talk about this. We're going to look at a quick view now of a defense system. This is from Suzuki, and it shows how the system is able to detect looking forwards and how it progressively alerts the driver via chimes and symbols that there is a problem, and ultimately the system will take over from the driver if the driver doesn't respond to those alerts. The Suzuki system is not the most sophisticated on the market. The most sophisticated systems now have the ability to not only auto brake but also to a limited extent auto steer to avoid impending accidents. So the system is quite sophisticated, and that's what I really want to get across on the next slide, because if we look at the next slide, it shows how the key building blocks for the brake system are integrated into the data system with the sensors. So it's smart enough to know that if we're indicating we're potentially maneuvering out of lane, if we have the wipers on, that will affect the braking distance. If we have the headlights on, that could affect visibility. All of these factors are included in, and also where impact does occur, ADAS does not always prevent impact. It is able to then queue up the optimum configuration of the windows, and they fitted the sunroof to minimize the shock wave caused by airbags going off, to pre-tension the seat belts, and also to pre-fill the braking system to minimize the response time. So this is an incredibly sophisticated system of which the sensors are an important part. So let's look now at the sensor aiming, and we're going to begin with what I call the tool room scenario, and this is used, I headline it with the German manufacturers, Mazda and more. Many manufacturers use this approach, and essentially this is defining the center line of the vehicle versus the center line of the sensor, and then defining some sort of artificial horizon. So it's a static process. It involves putting sensors on each of the four wheels to establish the wheels versus the vehicle center line, and then using a variety of devices in front and, if required, behind the vehicle to aim the associated sensors. This process is definitely something that needs to be done indoors. It has to be done on a horizontal surface. The devices that are used, and we can, if we look now on this next slide, we can see the kind of device that's used to hold the aiming board, the pattern that in this case the camera has to look at. This is not something that will withstand high wind speeds. It can be used outdoors, but we need good light conditions, we need no prevailing wind, and we need to have a level surface. Tick all those boxes, and yes, this could be used outside. This has been one of the stumbling blocks for the glass repair business because they need a mobile service to support their business. And at the moment, for the static process, that really doesn't wash. So we have to think this is transient. This is technology. You and I could go and buy a brand new vehicle straight out of the showroom right now that needs this kind of work, even though the technique is buried way back at the turn of the century. And again, we have another picture of some typical kinds of tools that are used during the process. And these are available to lease or rent from the vehicle manufacturers via their dealerships. There are aftermarket alternatives. We also have to realize that the physical setup is only part of the story. Diagnostics is crucial to this. We have a certain amount of mechanical aiming for the sensors, but the primary aiming is done electronic via the diagnostic system. So we have to have a knowledge, be comfortable with vehicle diagnostics in order to complete the calibration. And this is not about warning lights being left on or warning lights coming up on the dash. In diagnostics, the most important thing is to figure out what the vehicle is saying by way of fault codes and trying to find the root cause for the fault code in order to eliminate it. Aiming is important because if we don't aim, then the sensor will do its job by looking in the wrong direction. And because we have a very small range of, the sensor has to be built on vehicle centerline. If it's off vehicle centerline, then over a quarter of a kilometer, 250 meters, the error out at the extreme of the measurement zone could be more than a vehicle width. So this is rather important for the end user. And frequently, if the systems are fitted, calibration is a necessity, even if the sensor hasn't come off the vehicle. Just be aware, all the routes go back to the vehicle manufacturer methods and how to use their tooling. Another example here is from Toyota. This is a global platform. So we see already Toyota Prius 4 and CHR. These are already using the platform, also Camry, new Camry. And it means that just like the Volkswagen MQB platform, they're commodities that are used across brands, and therefore the architecture is common, even if outwardly they look like different vehicles. Specifically in the case of the Toyota, I'm going to look at a radar setup at the front. We can see directly that we need a lot of space. We need around 5 meters width, and we need a total of about 8 meters in front of the vehicle. So already we've used more than a car bay in order to have the aiming area in front of the vehicle. The good thing with the Toyota system is that it uses a full description in the vehicle methods, including, in the case of the camera, a target which can be printed out from the instruction, scaled up and used during the process. It's a little bit archaic in that it uses very basic measurement techniques in order to set up the aiming spots for the tooling. But in another sense, Toyota get full marks because they provided all the information, as did Mazda too. So if we then look at the aiming for the camera, we have a target board and it has to be moved through specific points in a specific order as part of the calibration. Remembering that whilst that's going on, whilst we're physically moving parts around in front of the vehicle, we're also using the diagnostic system inside the vehicle to complete the calibration process. The amusing thing is that we have arcs drawn on the floor with string and crayon or paint pens in order to set up the target positions for the target board. If we look now at another picture here, again this is the camera showing the order in which the device moves. And then we move on to the rear end, and again we have maths and trigonometry. Again we're drawing on the floor, and here we're using a reflector for the rear mounted radar if fitted. And it's a complicated process. So if we now look at the amount of area that's required, at the front, 6 meters long, 5 meters wide. This is in front of the vehicle itself. At the rear, a space 8 meters long behind the vehicle and 15 meters wide, including the width of the vehicle. So that means that for particularly body repair businesses, they could almost clear out a substantial area of the repair floor in order to calibrate the system. Is that viable? No. It's a way of dealing with the technology now, and as we'll see, this is not the future. However, in the aftermarket, we deal with all iterations from the very beginning. So we have to be aware as we move forward to the Holy Grail, which we'll come to in a little while, that we still have throwbacks like this. So Honda now, Honda Civic 10th generation, so effectively a new product from the beginning of this year. And again, we have the same routine, measurements in front of the vehicle. We have a reflector cone for radar sensing, radar setup. We have another device on the next slide, which shows the boards that are used for the camera. The same routine, physically setting it up. Here we have 7 meters ahead of the vehicle and 4 meters, including the vehicle width. That is a lot of space. And then we have on the Civic, for blind spot detection, they don't use radar. They use cameras mounted in the door mirrors. And here we have a space from the front of the vehicle, 6.5 meters long, so only a few meters longer than the vehicle, and 3.5 meters from the far side of the vehicle to the edge of the test zone. Again, that's an extraordinary amount of floor space, a static process. Okay, there is a future. In 2008, Volvo, Ford and others started a dynamic process. Here we have some very basic mechanical adjustments that can be done with a spirit level to ensure that the sensor is not at a different angle to the ride height, the unladen ride height of the vehicle. Beyond that, the aiming is done purely electronically, and it has 2 steps. One is to download software from the vehicle manufacturer's site, and then the second part is a driving process. Here we see Jaguar Land Rover, who have on Jaguars and some Land Rover products 2 cameras in a single module. By using 2 cameras, the camera module can triangulate the image, and therefore it can also measure distance as well as classify the object. Here we could see, using Ford as an example, the ETIS front screen. So we've logged into ETIS, we've paid a subscription to access software, and if we now move on, we look at the process. The first step is to download the software app. Then the system will run a diagnostic check through the whole vehicle. The system is smart enough to know what the vehicle has fitted to it and therefore what needs to be checked. In that process, it's updating the vehicle with all the software patches that have been available since the vehicle last returned to the dealer or the approved repairer. We know some manufacturers do these updates over air. So again, this is kind of a stretch. You could see how many iterations of software update have happened if what was considered cutting edge in 2008 is not cutting edge in 2017. The system then downloads a software patch for the calibration that we need to do. And that software patch has all the latest updates and is valid for 24 hours. Then, having got that software uploaded to the vehicle, we're ready for the next stage. If I just, so on the next screen, we need 2 technicians. One to look at the computer and one to drive the vehicle. Bear in mind, of course, it's not safe to operate a computer whilst driving unless you're on a private test track. And of course, we can't use the word test when we're out about anyway. Bear with. So we now need to drive, in this case, between 40 and 60 miles an hour. So immediately we have to start thinking about how can we find a place to drive between 40 and 60, and how long does it take us to get the vehicle and 2 technicians to that place to drive the speed. Like an old-fashioned Microsoft program, the program starts as soon as it sees the desired speed range, and it stops every time the driver either exceeds or falls below that threshold. In the process, the system is looking for a series of lines, a series of obstacles. So we can't just sit behind another vehicle for 20 minutes with calibration times between 10 and 30 minutes. We can't just sit behind a single vehicle with a single set of markings. It's looking for variety. And if it doesn't find that variety, the calibration halts until it does find something. So we've just added some variety into our process. Okay, let's assume that we've managed to get through all of that. The ETA system will then complete by doing a final sweep of all fault codes in the vehicle, and then calibrate any remaining static calibration items, and then restarts the whole vehicle system. Okay. Other manufacturers are doing this over air. Ford, on some products, are doing this by a wired system using their diagnostic system via the ETIS website. You can see the difficulties. A headline, 2 technicians, 10 to 30 minutes. The reality, if we think about central London, central Birmingham, central major city, that could look like an hour or 2 to get to a place to do the work, and then come back a morning. Worse, it could take a day. I think reality is, for most, it will be a morning. That's quite a lot of time. However, there is the Holy Grail, and that is self-calibrating, auto-calibration. And the first one I came across is on 3rd gen MQB platform, in this case Skoda Octavia, and it was the rear radar modules, clip it into the carrier, and the rear radar modules, if fitted, sort themselves out. On the same vehicle, if fitted, the front camera and the front radar need to be calibrated in the tool room way. So we see directly a mix-up of calibration techniques. The end game is self-calibration for forward-facing camera, for forward-facing radar, for LiDAR, for all sensors, self-calibration. Why? Because as this becomes standard equipment and therefore falls into potential warranty spend, you can bet vehicle manufacturers will not want to spend lots of time and therefore money doing calibration the tool room way or any other way except plug it in and let itself sort itself out. So there is a hope, there is a future. It's beginning to happen now, but we have a full range of solutions even on the very latest brand new vehicles that you can get from the dealer right now. So just a quick word about LiDAR. So LiDAR is the same kind of technology that would be used to measure a room inside a house. It's the same kind of technology. It uses a Doppler effect, so it's chopping the signal, just like radar, chopping the signal in order to then figure out relative distance and therefore, if we move the sensor, relative speed. And in the first generation, these were used for a single measurement, sub 10 meter, to fill in the area that was difficult to get radar to do when radar via different sensors within the same box is covering a range up to 250 meters. However, there's much, much more to come from LiDAR. LiDAR has the capability to scan in real-time terrain. This was what was used in the very first autonomous competitions back at the turn of the century, to map land in real time. Is that capability needed? No, because that's what maps are for. That's what map providers like TomTom and others are there to do. Of course, not forgetting Google. The power comes in that LiDAR can do what a camera and radar combined can do. And that means we haven't seen the last of LiDAR. Indeed, in 2018, Volkswagen Group will launch another version of LiDAR, which is preparation towards autonomy. Not autonomy, but towards. So we haven't seen the last of it. So the sensors that we see now are almost fit and forget. Yes, we occasionally have to consider aiming electronically via diagnostics, but it is not the whole story. So I want to talk about the future. So here's a picture of a Mercedes electric bus. It doesn't matter that it's powered by electricity. It could be powered by liquefied natural gas, by diesel, by all kinds of means and combinations of the story. 21 sensors allow this bus to travel at speeds up to 44 miles per hour without a driver. Now, I can tell you that I don't think there's anybody, either insurance company, local authority, bus operator, or anybody else that will want the seat where the driver should be to be vacant, But that is a first attempt. Why bother? Because an automated bus, a low-speed autonomous bus, makes more sense than trying to create tramways, and is cheaper, potentially cheaper on busy routes than employing drivers to drive buses. This is the very first beginning of autonomy, and indeed is a point that autonomy is going to appear first in the commercial environment and not in passenger cars. Passenger cars, the systems will be offered gradually as a feature, as something to almost, you could say, to play with. But the serious matter will be with trucks, long-haul trucks operating between distribution centres and buses operating in town centres. So what's in it for us? I think an awful lot. What the Mercedes program shows, which is going to be launched in 2018, is that we will see more sensors per vehicle. Today, if we see any sensors, it's ones and twos pointing forwards, ones and twos pointing backwards. Already some vehicles are offering, for example, 3 radar modules at the back. It's going to get more complicated. More of those sensors will be fitted to the glass, which suits manufacturing. The logic is the body is set up in manufacturing, the suspension is set up to the body, the glass is set to the body, everything is true. And glass is a very valuable commodity, it has to be treated very carefully. So it makes perfect sense to dress expensive sensor items to the glass and fit it in repeatedly in the same way on the production line. That gives us a serious problem in the aftermarket for glass repair technicians and also for collision repair specialists. Aiming will simplify, but is going to be centered around diagnostics. So we need to know about diagnostics. We need to get into that in a big way. As I mentioned earlier, heavy goods vehicles and some passenger service vehicles above 7.5 tons gross vehicle weight have had lane departure warning and auto brake fitted as standard since September 2015 for new types of vehicle. Like commercial vehicles, for new types above 3.5 tons will have lane departure warning and auto brake fitted as standard from September 2018. So, what do we need to do? So we need to access the CPD courses that are available via the IMI and others, particularly the IMI. It has a huge amount of information, useful information. We have to be used to educating ourselves all the time. We need an awareness of both current and impending system developments, because that will inform us when we see a vehicle. What do we need to do? It informs us how to triage, how to treat the vehicle, where to get information. And we need to use the IMI Professional Register as a membership as a way of promoting ourselves with our newfound knowledge. So to recap, in this session we have covered today the vehicle defense system, sensor aiming, which is all about look at the vehicle, find out what's on it and get the methods, get the information, some indication of the future, and then finally what's in it for us, which in this case is rather a lot. Thank you very much.